Thank you so much all for coming to join us on our the On-Farm Carbon Advice webinar series. Today we have Matthew Newell and Richard Meyer from the DPIRD Pastures team, and they will be talking to us about designing pasture mixes to reduce emissions in extensive grazing systems. Now, before we begin, I'd like to acknowledge the traditional owners of the lands and waters in which we gather today. I'm on Budjalung country on the north coast, and I recognise the continuing connection to land, water and community. We pay our respects to elders past, present and emerging, and extend that respect to all Indigenous peoples here today. For those who have just come in, this session will be recorded and it will be available on our DPI webinar series website that you all have registered on. So thank you. There will be an opportunity for questions at the end of the presentation, and so feel free to put them in the chat. At the end of the webinar, we will put a short survey in the chat. We'd love your feedback and so that we can keep producing more of this content. So let me introduce Matthew Newell and Richard Meyer today. So Matt has been working in agricultural research since 1994, and he brings a wealth of experience in pasture agronomy. So since 2021, he has been one of the lead investigators examining pasture species with low methane potential. We also have Richard Meyer, who's an analytical chemist and is what leads a team of technical staff in the Wagga Wagga Feed Quality Laboratory. Richard's currently leading a project on rapid assessment of methane emissions from consumption of pastures using near-infrared spectrometry. Okay, Matt, shall we kick off with you? Would you like to share your screen?
Thanks, Camilla. So hopefully you can all see that.
Yes, we can. Thank you.
Richard and I are going to tag team a bit through this presentation, covering off the different areas regarding reducing emissions through grazing systems. So bear with us as we move through the presentation as we go along. You would all be aware of the concerns about increasing greenhouse gas emissions and its relationship to climate change. And so emissions reduction plans have been a part of both state and federal government policies and legislation, not only in Australia, but across the world as a target to reduce emissions. But for industry bodies like Livestock Australia, they have also invested heavily in understanding the emissions profiles in the red meat industry and have set aspirational targets to become carbon neutral by 2030. And that's been used as a sign that to both consumers and the market that the red meat industry is proactive in addressing emissions across the production chain. So what does this mean for producers? So increasingly, the question has been asked, what is the greenhouse gas liability of production across the supply chain? And so as a minimum, it can turn up as a line in a report to Board of Management for different production companies. But there are also opportunities opening up for different markets for producers to put livestock products into. And an example of this is the recent carbon neutral range that Coles has released. And so for producers, there's market opportunities opening up around low methane production systems, which in the future may attract a premium. And of course, the other end of that scale is that governments in the Northern Hemisphere are introducing taxes on livestock production as a way of reducing emissions. And so if we can develop management programs that can reduce emissions in livestock production, will go a long way to stopping that type of system becoming introduced into Australian agriculture. And so the starting point for emissions reductions is to understand what the liability is for different industries. And this here you can see is a result of a recent inventory for the state of New South Wales, showing different industries and their emissions across their processes. And you can see that agriculture accounts for about 12% of the total emissions produced by the state. And 76% of those emissions come from animal production. So for producers to become involved in emissions reduction schemes, the biggest opportunity for them to reduce emissions is by tackling those that come from animal production, and that's in the form of methane. And so just to remember that, methane has about 30 times the heating power of carbon dioxide. So where does the methane come from? Well, methane is produced primarily in the rumen of sheep and cattle, and it's a natural product from digestion. So as forage enters the rumen, it undergoes fermentation as part of the digestion process. And as part of that fermentation, there's hydrogen released into the rumen. Now, if there's too much hydrogen builds up in the rumen, it creates a negative feedback loop, which reduces further fermentation. And so ruminant animals have evolved to have different pathways to try and manage and remove that hydrogen that's produced in the rumen. And one of those pathways is to turn it into methane, which is then burped out through the animal. And that process is an energy cost to the animal. And so if we can disrupt that pathway, there's more energy becomes available to the animal through digestion, and we can get a bump in productivity. And so most of the strategies to reduce methane is to either interfere with that process of production of the hydrogen or to promote those other pathways that use up the hydrogen without producing methane. And so you may be aware of a number of feed additives and technology that's come onto the market recently in an attempt to reduce methane. So these things include feed additives, so the methane inhibitors such as 3-NOP, aspergillus, which is a seaweed extract, and essential oils have been used or promoted as a way of reducing methane. There are some longer term strategies used in rumen manipulation, which is trying to change the microbiome in the rumen so that there's less of those microorganisms to produce the methane. There's also breeding targets within some herds to reduce or select for animals that are naturally lower in their methane production, and they tend to be more efficient animals. And then there are technologies like these ZELP collars, which supposedly can pick up the methane as it's released from the animal and turn it back into carbon dioxide and water. But 95% of the sheep and cattle production in Australia is from grazed pastures, so they're extensive systems. And so most of those technologies or the feed additives are more suited to the intensive form of animal production, to be used in feedlots and dairy and those types of things. And particularly around the additives, it can be difficult to deploy those in an extensive grazing system to make sure that all the animals can access those additives and consume enough to be able to reduce their methane production. But there are pastures that we can use that have an ability to reduce methane production, and they contain certain properties. Now, part of that story is producing pastures of higher quality. So higher quality pastures are more digestible, so they move through the rumen quickly, so there's less opportunity for rumen production of methane. But there are a number of species which contain what we call plant secondary compounds. And these are classified into 3 different types. So they're condensed tannins, saponins, or phenols. And they work differently in terms of how they affect those pathways for methane production in the rumen. And as you can see in that table off to the right, This is from a review that Warwick Badgery did into looking at what pasture species are available and the potential for reducing methane. You can see most of those species belong to the legume family, and there are some herbs which you might be aware of called chicory or plantain, and they all contain different amounts or different types of those plant secondary compounds and have various ability for reducing methane. And so the other part of the story in reducing methane is to examine it in terms of its emission intensity. So it's no point in just having an overall reduction in total methane production, but we still be able to need to maintain productivity, and so emissions intensity becomes important. So how much livestock production or how much meat production are we producing per unit of methane that's being released? And also by using pastures to reduce methane, we also have the ability to bring other traits across which are also important. So by using legumes in the system, we get a source of nitrogen, which helps productivity and increases feed quality. Having these plant secondary compounds also have other effects in terms of animal health. So they can reduce bloat, they can reduce worm burdens, and some of these plant secondary compounds have an antioxidant activity. So there's benefits not only from reducing the methane, but also benefits in terms of animal health for the livestock that we're producing. So this might be a good point to bring Richard in to talk more about the feed quality aspects and more detail of these plant secondary compounds.
Thanks very much, Matt. Can everyone hear me? Can you hear me okay?
Yep.
Yep.
Yes,
yeah, thanks very much, Matt. So I was basically just going to start off covering off on some feed quality characteristics that affect enteric emissions, and looking at these components I've got on the screen at the moment, and their contribution and what researchers around the world have found in terms of how much they contribute, etc., and the mechanisms, and then fold back into the role that plant secondary compounds have. I've got added supplements on there, but I won't cover added supplements, but I thought I would just include them in this screen because there is a bit of work going on in using supplements and trying to work them into extensive systems. However, as Matt mentioned, there's lots of challenges involved in that. Okay, so can't seem to progress my screen.
You might need to hit Alt-Tab and go back into PowerPoint or click on a slide, maybe. Have Zoom in the background.
Okay, that seems to have done it.
Great.
Okay, so to start off with, I thought I'd just expand on what Matt mentioned before and just have a look at this table, which covers off on a number of different strategies that researchers are looking at to reduce enteric emissions from livestock. And I've divided them into various supplements and feed quality and genetics and rumen manipulation, including what Matt was talking about before, probiotics and vaccines and some exciting stuff that's going on in that area. But if we focus in on the feed quality stuff, I've outlined it there. And I wanted to draw your attention to the typical methane reduction percentages that researchers are reporting in these various different strategies to try and reduce the level of methane. So we can see that some of the methane reduction percentages there in the feed quality area are fairly modest, I suppose. But there again, looking at some of the plant secondary compounds, there's the potential for some pretty exciting reductions there as well. So and also remembering that some of these feed quality attributes might be easier to manipulate than looking at adding supplement and working that into extensive systems. Okay, so looking at back at feed quality characteristics, the first one that I was going to look at was carbohydrate type. So this is really important to when looking at the amount of enteric emissions that we see. And the first carbohydrate type that we're looking at is fiber content. So normally when we're talking about fiber content, we quite often talk about NDF or neutral detergent fiber. And it has it tends to increase the level of emissions with the higher NDF we're looking at. But there's a bit more to that story which will unfold in the next few slides. Fiber has the tendency to slow down the rate of passage, which means that the feed spends more time in the rumen, and the particular flora that are consuming those fibrous feeds tend to give higher acetate propionate ratios, which, as Matt alluded to before, when you're producing acetate and butyrate, you're also producing hydrogen and carbon dioxide, and they're the ingredients that they're the goodies that the methanogens need to produce methane. Whereas when you're producing propionate, that's actually a net consumer of hydrogen. So of course, NDF is they're large polymers of sugar molecules, sugar units, and they're large and complex. They're cross-linked by another polymer called lignin, so they can be of varying difficulty to digest. And in years gone by, we'd looked at NDF minus the ADF fraction, which people generally think of as hemicellulose, and we thought that was pretty much the digestible portion. We've moved on from that level now, and people are talking about NDF digestibility, and we understand. To measure the NDF digestibility, we basically measure the amount of NDF before and after a rumen fluid digestion. That gives us a really good understanding of how much of that NDF or fibre is available for digestion. And the higher the NDF, the digestible NDF, the better the increase in passage rate, and you get better increases in production. But you can also actually get increased methane per day with that as well. But it can lead to overall lower methane intensities, which I'll talk about in a little bit more detail shortly. Yeah, progressing on to components of higher starch feeds. Obviously, concentrate supplements are higher in starch, but immature cereals can also be fairly high in starch. Once again, they've got a faster rate of passage, but the bugs that are consuming those also tend to produce more propionate than acetate as well. So you end up having a smaller proportion of acetate, and then so less hydrogen and carbon dioxide. But those highly productive feeds, water-soluble carbohydrate, the amount of sugars from pastures, that tends to be in exactly the same scenario. So that tends to produce a lower acetate to propionate ratio, but they're big, they're highly digestible, and there's more to that story, which I'll explore in the next slide. So I just thought I'd put this slide, this feature up on here as well, which shows that as we go down, and the carbohydrates become more freed up, more accessible, it's obviously a lot higher digestibility, and as we go back up towards the more fibrous feeds, we're higher emissions intensity. So just exploring that emissions intensity idea a little bit more. So obviously, the higher the proportion of digestible carbohydrate, the more total VFAs that you're going to produce. So regardless of that ratio of acetate to propionate, you're producing more VFAs, and in that scenario, you are likely to produce more methane from a feed. However, with that high digestibility comes a higher level of animal production, whether it be meat, milk or wool. And this is where the concept of emission intensity comes into play. I've just got a really simple stylized diagram here. So we've got lambs on a low quality pasture, lambs on a high quality pasture, with a time to their target sale weight on the bottom. So lambs that are consuming high quality pasture are going to have a shorter time to reach their sale weight, whereas lambs on a lower quality pasture are going to take longer. And for simplicity's sake, I have represented the amount of methane that's being emitted in a time period, a day or a week, in those bars that are on the side. And for simplicity's sake, I've made them exactly the same per time period, but with those previously discussed attributes, they could be higher or lower depending on the nature of the pasture. But regardless of that, we can see that those that are on the higher quality pasture are going to produce less methane over time, over the time that they're growing, and those on the lower quality pasture are going to produce more methane over the time that they're growing. So in this way, we're getting a lower emissions intensity with a high quality pasture, and the converse with a low quality pasture. Just looking at some other feed quality characteristics, moving on to protein and lipids. So we've got mixed results from the protein content from studies around the world. So studies have shown us that with the same energy content of a feed, if you have a higher or a lower protein content, you tend to see not really much difference in total methane emissions. However, the story there is that crude protein really needs to be sufficient to match the available energy so that the digestibility is optimized. If you have a lower protein content on that, you get a lower level of production, and then you'll get a higher emissions intensity. If you get a higher protein content then that's not matched to your energy, then we know that there's an expense involved with those higher protein contents, about 0.2 megajoules per percent above the optimal percentage of protein. And that also can lead to excretion of nitrogen through urine and higher emissions involved in that as well. When we're looking at lipids, moving on to lipids, so there's pretty good research to suggest that lipids has a pretty good role in lowering methane emissions, and particularly certain unsaturated fatty acids. And we know that they can be toxic to methanogens and to protozoa. And methanogens and protozoa tend to have a pretty good relationship, working with each other to create methane. We know that an extra 1% inclusion of lipid can reduce methane emissions by 3 to 5%. They have the addition of providing a different source of energy. So rather than volatile fatty acids, which provides about 80% of the energy to the animal, like lipids can provide an alternative source. And you can reach methane emissions reductions of up to 15 to 20%. But this is at the higher end of lipid contents, which are about 5 to 6%. If you have additional lipids on from that, then you start getting problems with fiber digestion. And getting back to that, so there's two ways that you can look at adding lipids into the diet. So a lot of lush pastures have fairly good lipid contents, and there's also things like cold pressed canola meal, which is a good source of lipids as well. But getting back to the pastures, we've definitely measured some pastures in the feed lab that some lush ryegrasses that have had lipid contents approaching 6 or 7%, which is huge. And Ed Clayton, I think, who is presenting at in a webinar in a following series, he's been looking at these fatty acid contents in the Australian feed-based context and been doing research on that for 10 to 15 years. So yeah, he's closely looking at this sort of stuff. Oh,
Sorry, Richard, I had a question from Bill Finlay. It said, is the digestibility driving the emissions, or is the subsequent lower growth rate really the cause, or is it both?
it's a bit of both, to be honest. Like you can get you tend to get lower emission in intensity, I suppose, with more like with a higher level of digestible carbohydrate, you're definitely going to get higher methane levels, but you're going to get better production. I suppose is the short story.
Awesome.
But that's outside of these other attributes, which Matt will be talking about a little bit later on, particularly like plant secondary compounds. Matt talked about saponins, condensed tannins, and polyphenols. They reduce methane emissions in different ways. So the condensed tannins, they bind up with protein and they create a physical barrier. And we all know that high tannin, if the tannins are too high, they can also limit protein availability. Saponins, they're directly toxic to methanogens, so they'll lower the number of methanogens that you have available to create methane. And polyphenols, they have an antioxidant effect, so they can disrupt bacterial cell membranes and basically make them less efficient. So now moving on to methods of estimating methane emissions from pastures in our research. So we've been looking, there's 3 different ways I'm presenting here. There's the in vitro system, which we run in Wagga, which is basically, we take rumen fluid from a donor animal, we ferment with the feed that we're looking at over 48 hours, and then we track the gas production, and we analyze the gases that are produced from that. And that's a really effective way of getting, we can get relatively high volume at a low cost through that system with good predictive ability. When I say high volume, we're looking at about 15 odd samples a week through that system. Then we've got the methane collar green feeder option, which basically measures the methane that is being expelled from the animal by putting on a collar or measuring the methane expelled from their breath during a feeding activity. And finally, you've got a respiration chamber, which is the gold standard, where you're measuring methane that's evolved from the animal over 48 hours within a confined space. So that's very slow because you need replicate animals, and you need to have them condition on that feed over a week or so prior to putting them in the chamber. So we've chosen this system to look at some of the mixed pastures that Matt's going to be talking about. I'll briefly run through this system again. So this is just a couple of pictures that put that together again. So we take rumen fluid, we add it to some dry ground samples that are within jars, freeze-dried samples. We incubate that for 48 hours, and then we measure the methane that's evolved. So this is actually part of a project that I'm heading up that's looking at a more rapid way of estimating methane output from pastures. So we're taking 1,000 odd samples and we're running them through that in vitro system. We're also scanning them through a NIR spectroscope, and then we're producing some NIR calibrations from that are going to allow us to measure, say, in 30 seconds or a minute, estimate what the output, what the methane emission would be from that particular pasture. It's going to have benefits in allowing some early stage selection, but it's also going to be an enabling tool for some of these other grazing studies and closer looks at forage and mixed species. That's just a picture of an NIR. These are some early results from samples from Guangdi and Matt's project, looking at individual species, and right from the get-go, we could see some lower methane emitting species in there. So this was just to sort of demonstrate, some of the results that we first started seeing. And we've progressed on to there to having a look at a whole range of samples that are coming through the feed lab. So we're looking at, as I say, looking at 1,000 samples all up. We want calibrations that are going to be able to handle samples in the real world. So it's important that we're looking at samples from the feed lab. But also, this gives us a real opportunity to have a look at some of the practices and some of the samples that are coming through, and to case study some of those samples and say, okay, well, why is this particular one giving a low value, whereas the same sort of sample produced elsewhere is giving us a higher value. And this is some early model NIR calibration stuff that we've we were up to an early model, I suppose, that is sort of showing proof of concept that we are going to be able to get some useful tools in here. All those different colours in there represent different forage types, and so ultimately we'll probably have some different calibrations representing different forage types that'll give us more accurate models. But this will really help us measure stuff into the future. And this is about the time where I switch back to Matt's presentation so he can talk about some of the results from his mixed species stuff.
Great, thanks, Richard. Matt, fabulous.
Righto, thanks, Richard. You can all see that again, I hope. So yeah, just following on. So we've then conducted some trials looking at mixes of these different species that have potentially have a low methane or methane reduction ability. And we conducted it at 2 sites. So we had Cowra in the central western New South Wales and Wagga down in the Riverina. And there was 2 trials. So the first trial was established in 2022, and it used 4 main species as chicory, tall fescue, phalaris, and plantain. And at Wagga there was an extra treatment of cocksfoot. And each of these species were then mixed as a 2-way mix with these particular legumes. So we had Balanza clover at Cowra, we had 2 types of Ceradella, a Bicerula, a subterranean clover in Lucerne, and an extra treatment of arrowleaf clover at Wagga. And the second experiment, which was conducted at Cowra, used those same 4 main species, but used the perennial legumes in the mix. So either white clover, lotus, sainfoin, or sulla. And so overall there was 53 pasture mixes investigated in total as binary mixtures. So a 2-way mix between either the legume and those main species. So the findings, we took average dry matter, which was measured seasonally. So every 3 months we took a biomass assessment, and that was done over the 3 years of experiments at both sites. We tended to see higher productivity at the Cowra site compared to at Wagga. And across both sites, chicory was the best performing pasture, and it was the most productive. It also had better complementarity with the legumes that we were using. So we tended to see better legume growth when it was mixed with chicory in the pasture compared to some of the other main species. And we also had showing that complementarity with the chicory, we had that higher legume content, and at Cowra, so we maintained 30% legume when we had chicory as the main species in the mix. The poorest performing species was for plantain, and mainly this was due to declining plant population, and it didn't perform well with some of the higher producing legumes, and that was at both sites. So plantain is more suited to a cooler environment and one that has sort of wetter summers than when we were trying to use it at Wagga or Cowra. And we found that it was mainly using seedling recruitment for its persistence. And so this is just a photo of one of the plantain plots. You can see those bigger plants are the individual plants that survived over the summer, But most of that green you can see in that plot is new seedlings that have come along. And so that's how plantain was maintaining itself within the plots that we had at both sites. This is just a representation of the productivity of those different pastures. So this is cumulative biomass over the 3 years at Cowra. And these are stacked graphs. So each bar represents the total production from the particular treatment. And so we had those 4 main species in tall fescue, phalaris, plantain, or chicory. So that's represented by the blue portion of the bar. The orange portion of the bar is the legume content. So whether it was Balanza clover, Bicerula, subclover, the Ceredellas, or lucerne. And you can see that particularly at Cowra, the best performing legumes were from Balanza and the 2 Ceredella species that we had in the trial. So they performed across all of the main species combinations. Those 3 legumes were the better performers. And as luck would have it from richer results, the legume with the biggest potential for reducing methane production had the lowest productivity in our trials. So that was Bicerula. So for the Cowra environment, Bicerula is quite short maturity, so its productivity is limited in our environment, but also likes areas that tend to be drier than warmer than the Cowra environment. So Bicerula didn't perform that well at Cowra. Similarly, we saw at the Wagga site, the chicory again was the best performing pasture species in combination with the legumes. The legume production at Wagga wasn't as quite as significant as what we saw at Cowra, and so the better performing legume species tended to be lucerne, which had dominated some of those components, particularly when it was mixed with plantain, phalaris, or cocksfoot. And Bicerula tended to do a little bit better in terms of productivity at Wagga compared to Cowra, because Wagga's a drier site. And that's following on, looking at those perennial legumes at the Cowra site. Again, these are stacked graphs. So this is the average production over the 3 years, again for chicory, phalaris, and plantain and fescue. Again, we saw that chicory was the better performing pasture when used in a mix. And of the perennial legumes, white clover and lucerne were the better performing species. And lotus didn't perform very well in that environment. So again, it's suited to a higher rainfall environment than Cowra. And the one to watch was a species called sainfoin, which you may not have heard of. No longer commercially available. It performed reasonably well in combinations with in those different mixes. And again, I think it's a species with greater potential for our grazing systems, not only because of its ability to reduce methane, but it's also a low bloat forage, and the flowers have a significant opportunity for honey production, so it's liked by bee producers. And just finally, looking at emissions intensity story. So again, because we know the productivity of these different pasture mixes, and from Rich's work showing us what the potential was of the different species for their ability to reduce methane, we can model emissions intensity through grass feed. And so in these charts, I've graphed out emissions intensity in terms of the kilograms of carbon dioxide equivalents per kilogram of live weight gain along the bottom there. And on the side axis, we're looking at the live weight production per hectare. And as you can see, phalaris subclover, which is a standard pasture mix used throughout industry, tends to sit to the right on the graph. So its productivity is sort of in the middle of the road and has high emissions intensity, compared to some of the other mixes. All of the chicory mixes tended to be at the top of this graph and to the left of phalaris and subclover. And that's mainly driven by the high quality in chicory, so it increases the animal intake, but then also has this ability to reduce methane. So we get less emissions in intensity, but higher productivity overall. And the other trend that we see was that all the mixes with Biocerula tended to be at the bottom of the chart. And that's, although the Biocerula was effective in reducing emissions, so lowering the intensity, its productivity wasn't as good as, say, chicory and some of the other clovers. And so overall, live weight gain in the animals was lower. And similarly, we can look at the same sort of chart for the wagga production system. Again, we're seeing phalaris and subclover off to the left, off to the right of the chart. So lower productivity, higher emissions intensity. But again, we're seeing that same trend in that the chicory mixes tended to have higher production at lower emissions intensity. And again, things like Biocerula, lower productivity, and those type mixes with Biocerula tended to fall to the bottom of the chart, having lower emissions, but overall production was lower as well. So in conclusion, then, we've identified the pasture species with potential for lower emissions. We've found that there are complementary combinations, particularly combinations with chicory, perform very well, giving us high productivity in terms of pasture production, but still an ability to reduce methane. We've identified, regionally adaptability for these different species and different pasture mixes. So chicory tends to be adapted to drier environments. It also does well in higher rainfall, whereas plantain is more suited to a higher rainfall, cooler summer environment, but still has that ability to reduce methane. And again, Biocerula, not overly suited to the environments where we were trying it in, but more suitable to those drier environments with warmer summers. And so the next phase for this experiment is actually to do productivity and methane production measurements on animals that are grazing by the use of these portable respiration chambers. And that will give us a better idea of how these mixes perform in terms of the ability to reduce methane, but also be able to measure the productivity of those animals. And just finally, it takes a big team to run these experiments, particularly over multiple sites and the multitude of investigations and experiments that we run. So it's a big thank you to the team that stands behind both Richard and I to be able to pull these types of projects off. And that brings us to a close. Thank you.
Fabulous. Thank you so much, Matthew and Richard. That's great. So do we have any questions from the room? I have one from Rowan. Rowan, would you like to come off mute and ask your question?
Sure. Thank you. Thanks, Matt. Thanks, Richard. Really great presentation. Really enjoyed it. Just interested, Matthew, in what you're seeing with chicory after 3 years, particularly in those in the challenging drier environment, and then also whether you ran into any difficulties in mixes and being able to get weed control if there was weed problems.
Yeah, I mean, so we've found the chicory persistence quite good. So it's and productivity probably better than phalaris. So particularly over the last couple of years, we've had a couple of dry summers, and we're sort of maintaining those experimental plots, still recording dry matter. So dry matter production. Chicory is still persisting really well. It's still the top of the production productivity, and we're seeing that better complementarity between chicory and the legumes that we're growing. So even in a drier time, we're seeing that the legumes that are mixed with the chicory are performing better and still looking turgid and fresh compared to the next door plot where it might be mixed with plantain or phalaris and the legumes are really struggling. So we think chicory is probably the key pasture species to include in these mixes. In terms of herbicides, yeah, herbicides are an issue for chicory-based pastures and for biocerula as well, but we can use broad strike on chicory, and it's still safe with most of the legumes.
Thank you very much. Bill, would you like to come off mute and ask your question?
Hopefully I'm off mute, but yeah, my question is, if I go out there and plant some chicory-based pastures, how am I actually going to be able to quantify the benefits of those? And then when I pass my product down the food chain, am I going to be able to say, this is a chicory-based pasture, or this is grown on a chicory-based pasture? What's your thinking in that space?
So I guess once we've been able to confirm and demonstrate that we can reduce the emissions from animals that are grazing these pastures and look at their productivity as well, then you'll be able to apply those results into the accounting budgets for the emissions reduction schemes. And so companies like Coles or that may develop that market, that may offer a premium, will have some sort of calculator to show or to ask you to identify your emissions and how you're controlling them, and you'll be able to plug those values into those calculators to allow you to access those markets as they become available.
Just to add on to that too, Bill, the idea behind this enabling tool, this rapid enabling tool, is to be able to have feed labs have access to that ultimately as well, and give some indication as to if there's a low emitting, if the pasture is low emitting or not.
So you mean I'd be able to get my feed sampled?
Yeah, exactly. The idea is that in addition to a feed test, you might be able to get some indication off some of these models for if that's like how low, potentially low emitting that is.
Because currently most of the models within the GAF tools draw some very broad conclusions about your digestibility and feed conversion rates. So yeah, drilling down into that a bit further would be very helpful. I'm sure not everyone's average.
Yeah, and so once we can get some indices about what these pastures can do in terms of the ones that have got the plant secondary carbohydrate compounds, and then be able to plug that into those models to give an indication of the animals have grazed it over this period. This is the likely methane production.
Thank you very much. Jeff, do you want to come off mute and ask your question?
Oh, yeah, look, thanks, Matt. That was really interesting. I was just wondering, I noticed with lucerne and some of the grasses flourish in those mixtures, and I was just wondering whether you have an opinion on grazing impacts on some of those mixtures and survival or change in composition.
So we've been sort of monitoring that, and we probably wouldn't recommend mixing lucerne with chicory because they're too competitive. They're trying to use moisture at the same time, and lucerne will tend to start using that moisture earlier in the season than the chicory, and so that's why some of these other annual legumes are a benefit there, because they'll supply that nitrogen earlier in the season and then sort of disappear when the chicory is trying to survive over summer, but you still have a species present in the ground that's got this low methane potential. And yeah, grazing management with chicory is needs to be changed compared to other grass pastures. So it needs to be more of a rest during the cooler months, but really hammered hard during the spring to maintain the quality. And chicory's also got that benefit that it can recruit from seed. So you can maintain the population that way as well.
Now, we're 6 minutes to 2. I just want to say thank you so much to both Matthew Newell and Richard Meyer for their really informative session today. Please register for any of the other sessions we have coming up. It is recorded. It will be on our website. I am just going to put our survey in there, and I will also share the survey details. We'd love to hear what you thought of the session. So thank you very much.
Thank you.
Thanks, Camilla.
Great session, guys. Well done.
Thanks, Bill.
Thanks, Camilla.
That's right.
Thanks, Matt.